once we got that started, we'll go ahead and begin. Okay, so now that we're recording, I want to start today by talking about some of the things that we have due coming up and kind of looking ahead in terms of what's coming up in this class. So the first thing that I want to note is this week we are going to be having a lab meeting. It will be online, and we'll be discussing the project that we'll be working on. The project will be a group kind of, basically it's going to be like a lab report that you're going to do. It's going to be focused a little bit more on design and kind of computation rather than being in the physical lab itself. So this is going to be more or less a kind of a project. We'll talk more about it in lab tomorrow. I'll set up the Teams call so you can call in. So it might let you know for those of you who are on Thursday or Wednesday's lab. Day, you don't have to attend it. You'll get the same message for the people who have it on Tuesday about lab on Wednesday. So I just wanted to let you guys know that it will be online, so don't plan to come in because what I want to do is I want to introduce the project in that lab period, and then I'll let you guys work on the lab in your individual lab groups. Or if you want to, you can work on your lab 3 reports during that time period as well, because remember lab 3, which is the psychometric lab, is due this week. So make sure that you are still working on that. But again, you'll have maybe a little bit of time if you want to finish that up during the online lab session, either on Tuesday or Wednesday. So again, we'll talk more about the project in lab, but I just wanted to let you guys know about the fact that we'll be having things online. The next thing I want to point out is midterm number 2. It is sneaking up on us, and that will be happening next week in lab. So this will be week 8. Hard to believe that it's already week 8. This term is going very quickly. And so we do have this exam. This exam will focus on psychometrics and combustion. Those are going to be the main topics for this upcoming exam. This exam procedure will be the same as what we did for the first exam. So you have the equation sheets. I'll provide any extra references. It will be done in person in your lab period. Again, that will be next week's lab, and it will be in person. For midterm number 2, you should be able to find a module on Canvas for this. It will have some review problems, some parts that you can kind of study for a review sheet. So do take a look at that. Kind of covers all of the concepts that we'll be covering. Basically, the short answer is it's going to cover everything up through homework number 6. But again, we'll focus partly on combustion, partly on psychometrics. And again, some example problems from old versions of exams and quizzes have been posted. So if you do want some extra problems, you can take a look at that. Otherwise, the last thing I want to note is homework number 6. This is due next week, but it also includes some of the problems that we would have had due this week, but I just lumped all of combustion together, and you're just having one homework assignment on that. So there is going to be a little bit longer time for this homework. I think there's a total of like seven questions, including some concept questions in there as well. So do take the time to start that early as we kind of get through some of the material, start kind of working through it, particularly at this point we should be able to do the stoichiometric problems. So do try and start that so you're not feeling rushed at the things are going to get a little bit more intricate and things are going to start taking a little bit more time to complete. So start early on the homework. Okay, so that takes care of all of the general announcements. I know that's probably a lot, but at this point, let's go ahead and dive into our discussion about combustion. In particular, we want to get into the first law. And so what I want to do to start this discussion is I want to go back to Thermo 1. And for Thermo 1, if we had kind of an open system, well, we could say we had state 1 here. We could say we had some sort of heat transfer. We'll do the standard approach as heat transfer in. And then we could have some sort of state 2. If we recall from that analysis, we could say, well, the mass flow rate, if we have a single inlet, single outlet, that just becomes a constant. And if we let kinetic energy and our change of potential energy basically equals 0, what we ended up with was for a single pure substance, we had, it was the mass flow rate, or we should say Q dot, in this case, Q dot N. This would equal the mass flow rate times enthalpy 2 minus the enthalpy of 1. And so this was the setup. In this case, we had our pure substance. That could be CO2, it could be water, it could be air, it could be steam, whatever we chose it to be. We had that, and we just had to look in this change in the enthalpy. But again, this was for a pure substance. It worked because we had water coming in, we had water leaving. We maybe changed the pressure, we changed the temperature, and so we were able to basically use the enthalpy, which we said, well, this would be U plus PV, and so we basically had some sort of energy associated with the kinetic energy of the molecules. We had some pressure dependence in there as well, but generally this was kind of like the molecular kinetic energy. And so this is still almost all just thermal energy. Okay, so that's what we've done before, but now we're going to change things up a little bit. What we want to do is we want to take our fuel that we're going to bring in, nitrogen. And so this could be state 1, this could be state 2, and what's going to happen is we're going to go through a chemical reaction. That chemical reaction is going to change the molecular structure, and in terms of our products, we're going to have water, we're going to have carbon dioxide, we'll have some nitrogen, and we'll have some oxygen generally as our main products. And so what we see is, unlike our thermo 1 approach where everything stayed in the same kind of chemical structure, now we're basically going to be destroying fuel, destroying air to have some extra nitrogen. So if we want to think about this combustion, this is going to destroy fuel, and we'll also note that it can destroy the air, and then it's going to create the products. And so we have this energy now that's going to be associated with the creation and destruction of these elements, and we need to do this. And so what we want to do is we're going to change how we discuss enthalpy. In terms of our energy balance, so if we kind of still wrote out our energy, conservation energy, well, we could still say, in this case, we'll have some, maybe we'll do some heat transfer. Let's flip the direction of this. We'll do heat transfer in. And so we'll still have the same form, 0 equals Q dot N plus now the sum of the mass flow rates times the enthalpies on the inflow. Now the inflow will be the reactant side, and now we'll still have to, and the outflow would be our products. However, we now have to figure out, what do we mean by this enthalpy? In thermo 1, we just talked about the internal energy. It had its flow work that was associated with it, but that's no longer going to be enough for this portion of the class. What we need to do is we need to talk about energy. So if we talked about a change in energy, it's no longer going to be just a change in energy of the thermal portion, or we could call thermal our state, but that's associated with the chemical. And so chemical structure is going to be our reaction portion. And so what this means is that in terms of the enthalpies that we're going to have, and this is true of both the reactants and the products, the enthalpy is going to have a state portion. So the state portion is going to be our standard thermal portion. And then we're also going to have an enthalpy component that is related to the chemical structure and the chemical portion of the system. And so we'll note that the state pressure, temperature, and the chemical is going to depend on the chemical composition. And so that's going to be the direction that we're headed. However, there's actually a little bit more to it. There's actually one more step that we have to do, and it revolves around this H of the state. And so if we thought back to Thermo 1, when we introduced the tables, when we introduced all of those reference lookups, we said that, well, we may have heard it, depending on who you had, that all of the tables, everything that you've done with all of that, that's all. If you looked something up in the table, there was some reference value that it used, and that reference value could be whatever the table maker decided to use for that point. Now, why this is important is if we now think about all of our different tables. So if we have something for oxygen, we have something for nitrogen, carbon dioxide, water, whatever our fuel is, all of those could have different reference states in those tables. And so we can't just look up the enthalpy in terms of this state. We need to know what was the reference value that it was using. Looking at this, and so this is looking at refrigerant R1 or R744. R744 is actually just pure carbon dioxide, so that is the refrigerant name for it. And we can use different reference standards to take a look at what's happening. Now, what I wanted to show here is if we use the same reference that your textbooks use, which is the DFT standard, we calculate two different states. So we have a pressure 1 at 200, temperature at 300, pressure 2 is still 200, temperature 4 or 2 is 4. We look at the delta H. Well, if we go ahead and run this calculation, delta H is going to be 108.9. We'll look at H1, that's going to be 264.2. Now, if we change that and we instead choose to use the ASHRAE standard, so the ASHRAE tables are the American Society of Heating and Ventilation Engineers, we see that the enthalpy at state 1 has now changed. It's now 658.1 kilojoules. So the absolute value of that enthalpy changed. But we ended up having the same value. So it's got the same relative values, but we could have different absolutes. And so if we wanted just to show this one more time, since we can have some different standards here, we can do the same thing. We see again, delta H is the same. However, the two individual values of enthalpy changed. Now, if we wanted to visualize this a little bit, this is going to be a pH plot. So if you remember those from our discussion of the chiller system, we have the pressure and now we have the enthalpy. And so in this is the IIR reference. And so we see that the enthalpy is 0 somewhere in the saturated, or I should say compressed liquid region of the table, generally at a very low pressure, and it just scales from there. Now, if we use the ASHRAE standard, the ASHRAE standard sets the 0 point at a specific pressure at the saturation liquid condition. And so that can change from substance to substance. So that's a substance dependent value. It just happens to be that this one should be right about here. This side would give us a negative enthalpy, this side would give us a positive. And so if we do this last time for this last value, we can see that this case, it put the 0 enthalpy in the superheated vapor region, and we ended up having everything inside the vapor dome now is going to have some sort of negative enthalpy. But having a negative enthalpy is fine as long as we're using it with a relative value. So we have to still look at that delta H like we did here instead of just the absolute enthalpy. And so that was a little bit of a review from stuff from Thermo 1 about why making sure that you use the correct. Now, why did we do that? Well, we're still looking at this H state here. And we said, well, from our little bit of a discussion there, we can't just use the enthalpy at pressure and temperature. We have to use a delta H at this point. And so what we're going to do is we're going to choose a standard reference to be the second enthalpy that we want. And so what we need to do is we need to choose that standard reference point. Define that the reference temperature is going to equal 25 degrees Celsius, and the reference pressure for this state, because we need two independent variables that are both intensive to define it, is going to equal 1 atmosphere. If you wanted, that's 101,325 kilopascal, and that would be like 14.7 psi absolute. And so that's going to give us the reference state to help us out with this value that we're going to come together and be able to create is that the enthalpy at any given state, so enthalpy of temperature and pressure, this is going to equal the enthalpy of that state that we go to the table and look up, temperature, pressure, minus the reference value. So this is going to give us the delta H. So now we have the absolute amount of enthalpy for that value relative to a standard substance or standard point. And then we add plus, and then we'll have this chemical energy that we will do. Now what we're going to do is we're going to add one more thing here. We're going to add some bars on top of this. Now, why are we adding bars on top of this? Well, we recognized that when we did the stoichiometric balance, we said this was going to be a molar problem. And so now we're going to have to talk about our energy in terms of a molar energy. And so this is the form that we're going to want to do. Now, what we want to look up at this point, and what was really nice, is now we can focus on this chemical energy standard reference. Now, why is this important? Well, let's think about this. If we're creating a substance, this chemical energy is going to be the energy that's required to make that molecule. And we'll define this at the standard reference. So at 25 degrees Celsius, at 1 atmosphere, we can create this substance, and this will tell us how much energy it took to create that substance. We can figure out how much energy it took to move from the creation point up to the actual point. And so now we have an kind of more or less an absolute amount of energy that is associated with creating the molecule and then getting it to its state. So that's what this enthalpy with this kind of delta H plus, so this would be a delta H plus an H. That's what it's trying to say is this is the energy it would be is required to create it at the standard reference. This is the to the actual state point. And so where enthalpy was just one lookup before, we now have 3. And just to give you a hint of where this is going, we're now going to have air, fuel, water, CO2, nitrogen, and oxygen. And so there we go. We got more enthalpies to look up than we had before. And so what we want to do now is we want to focus on this chemical energy. So we need to focus a little bit more and get into what is the chemical energy that is required to create this, basically create a molecule at the standard reference point. Now, the simple answer to that is we're going to change the way we discuss that chemical energy, and we're going to redefine it as H with a bubble and F, and that value is going to be what we refer to as the amount of energy in the chemical structure that is required to form that molecule. So enthalpy of formation, because we're forming the molecule. And so this is the form that we're going to write out in the actual setup. Again, we note that it still has our delta H in terms of the state point. So this is delta H of the state. And we'll put a bar above it. Then we had the H chemical. That becomes the enthalpy of formation. and then the total enthalpy is just equal. Now again, I want to point out H bar, the units on this will be a kilojoule per k mole in the SI system. So again, molar basis for this analysis. So we do have to keep track of everything that's going on because it's going to be very important to keep track of our units, because we will eventually want to create a mass balance or mass basis as well. So okay, so let's go ahead and focus in and talk about what is this enthalpy of formation and look at how we can use it, how we can maybe kind of think about it in a very simplistic state. And so what I like to do is just use an example, and we can kind of talk through what the enthalpy of formation is and what it means. And so if we were to say take carbon, we were to take some oxygen, we put those two together, and we use those to form carbon dioxide. And then we said, well, according to our standard thermodynamic setup, heat transfer is going to be coming in. And so we're going to have some exchange of heat to have this process occur. And so what we want to do is we want to take a look at this creation of CO2, but we want the entire thing to happen at the standard reference. And so the standard reference means that the temperature at the reactant side is equal to the temperature at the product side, which is now also equal to the reference temperature, 25 degrees Celsius. Now, what this is going to do is, well, eventually we'll be able to show this. This means that we can take the enthalpy with the pressure and temperature minus the enthalpy of the reference point. This delta H for the state side of things goes to 0. And so all that means is we have the temperature on the reactant side and the temperature of the product side. We could also say that this is the pressure here is going to equal 1 atmosphere. But basically, would be released. How does this relate to the enthalpy? Now, what we can do is we can say, start this out by doing a stoichiometric balance. And so in terms of the stoichiometric balance, we have C plus oxygen. This goes to CO2. And we said, well, if we want one CO2 molecule, that means we have one carbon and we have one oxygen over here. That ended up being pretty nice. But we're also going to note that we're going to have some energy over here that we need to deal with as well. So this is kind of basically what we're going to be getting at as we want to look at this energy component. Now, what we're going to do is we're going to go ahead and apply our conservation of energy equation, and this is what we want to do. We want to do it on the molar basis. Now, for the molar basis, it's going to look pretty similar to our mass-based open system analysis. Anywhere we had mass flow rates, it's just going to become mole flow rates, molar enthalpy, and it all ends up working out. And so assuming we don't have any work, we can neglect kinetic and potential energy. What we're going to show is we'll have some heat transfer rate in, then we'll have plus the sum of all of the molar flow rates. And when I say the molar flow rates in are all going to be on the reactant side, times then the enthalpies that we have on the reactant side, minus the molar flow rates out. So this would be the molar flow rates. This would be our product side. And then we have the enthalpies of our product side. So that is the kind of simplified setup that we have. Now, if we go ahead and expand this out, we'll have 0. This is equal to Q dot N. Then on the times the enthalpy that's going to be associated with the carbon, plus now we'll have the molar flow rate of the oxygen coming in times the molar enthalpy of oxygen, minus now we'll have the molar flow rate of CO2 times the enthalpy of CO2. Now, what we'll recall is all of these enthalpies that we have. This would be H, temperature, pressure, state, minus H ref, plus enthalpy of formation. And so we'll put a bar above that. We said these two cancel each other out. So really, this is just going to equal the enthalpy of formation for each of these substances. Okay. So now let's go ahead and try and solve for this enthalpy of formation. So this just becomes enthalpy of formation for CO2. And so resolving this, we have the enthalpy of formation for CO2. This would equal, and now because we switch things around, this is going to be Q dot N over at the molar flow rate of CO2, plus then we'll have the molar flow rate of the carbon divided by the molar flow rate of CO2 times the enthalpy of formation of the carbon, plus then we'll have the molar flow rate of the O2 divided by the molar flow rate of the CO2 times the enthalpy of formation of the oxygen. And so that will give us the setup. Now, what we're going to do is we have to look at some of the enthalpy of formations for the carbon and the oxygen. And so what we're going to see is if we do this, well, in the next slide here, we happen to have the enthalpy of formation table. And so where do you find the back of your textbook? Table A26 has the value. We're going to come over here. This is the enthalpy of formation. And so we're going to find carbon right here. Carbon has a 0 enthalpy of formation because it's going to be a stable molecule. It's not going to take energy to form it at the given temperature and pressure. And then we can look up oxygen, O2. We're going to see that that's also 0. And so if we go ahead and do this, this goes to 0, this goes to 0. And what we're going to end up being able to solve or show is that I'm rearranging this. We'll have a Q dot N over N dot of the fuel. This would be of CO2. This is equal to the M for the, and looking that value up, carbon dioxide is right here, minus 393,520. This is minus 393,520. Units are going to be a kilojoule per k mole. And so that gives us the amount of energy that it would take to form carbon dioxide. Now, we'll note that the enthalpy of formation here was negative. Now, what does that mean? Well, let's just go ahead and rewrite this one more time, doing another Thermo 1 trick, and that was if we had heat transfer in, since the heat transfer in is equal to this, we could flip this around. We now have minus heat transfer out over N dot CO2. And what we see is the minuses will cancel. We're going to have heat that is released as we take oxygen, combine it with carbon to form CO2. And if we have heat being released, that means a minus enthalpy of formation at the standard point. This means that it's an exothermic process to form the substance. So that means we have Q out. And if we have a positive enthalpy of formation, it means we have endothermic. Which means that we'd have to put heat in to form a given substance. And so this is going to tell us a little bit about what's going on. We can see that we can now relate how much energy is going to be exchanged in this process. Traditionally, that energy will be talked about in terms of heat. Now, it also can be done that this enthalpy we could refer to as the enthalpy of combustion. According to your textbook, that's kind of just an introductory term. we'll just generally focus on the enthalpy of formation for this process. We'll be able to see how much energy is exchanged at the standard pressure and temperature, so we can determine the amount of energy that's going to be released. So is on just using this enthalpy of. Now, one thing I do want to point out at this point is we've so far focused on open systems whenever we've been talking about our energy. If we deal with a closed system, yes, if we go back here, we can see, well, the only thing that we have is enthalpies of formation. We don't have internal energies of formation. And so if you ever have to deal with a closed system combustion analysis, of course, would need the internal energy. What we're going to do is we're going to recall that from definition, H is equal to the internal energy plus PV. We note that H is going to equal H of the state minus H of the reference. The enthalpy of formation. And so resolving this, we can now resolve this and say, well, this is going to equal the enthalpy of the value, which is again the combined portion, minus PV. And so in this case, the V has to be the specific volume in terms of the molar quantity. So again, we'll put a bar above that. And so now if we wanted to go ahead and combine these, get internal energy, the internal energy is going to be a little bit more complicated because now you have the enthalpy that's going to be related to the pressure and the temperature minus the now reference state plus now you're going to have the enthalpy of formation minus now the pressure times the molar specific volume. Just using enthalpy outright. Mostly, though, we'll be focusing on open systems for our chemical reactions, so that's how we're going to approach it. But I do want to point out how you can modify it to get internal energy in this process. Okay, so we've already talked about where to find all of these values. So if we take a quick look here, you can see all of the different fuels that we have. We have carbon, we have nitrogen, we have oxygen, we have carbon dioxide, we have water in both liquid and vapor forms, and then we have a whole bunch of fuel. And so we'll be able to now look up all of the enthalpies that we have and enthalpies of formations, and we can now just go ahead and use those. So that is where we'll find those. Now, what we want to do is get into how are we going to apply this for the first law. Now, for the first law, we are generally going to have to make some assumptions. So we have to assume certain things. Now, we're going to generally assume for right now that we're going to be dealing with an open system. And this is going to and the more important one, and we'll see why this is very important, is that we can treat everything in our combustion process as an ideal gas. The result of this means that we'll be able to take our enthalpies and the molar versions, and these are only going to be a function of temperature, because that was one of our statements of ideal gas, is there's no pressure dependent portion. And so this is going to make our lookups a little bit easier in our life, that much simpler. We no longer have to worry about the pressures or partial pressures of each component. We just care about the temperatures to figure out what's going on in terms of energy. So that will help us out quite a bit. And so we're also going to want to go ahead and say the kinetic energy going to be pretty small. And so if we think about it, we said most of the time when we dealt with thermosystems in Thermo 1 and Thermo 2, we said we could neglect those because those were already 3 orders of magnitude smaller. It's about to be a whole lot smaller once we get into chemical energy, because we're basically giving more energy to that enthalpy term. And so a lot of times kinetic and potential energy can kind of be hand waved away unless you're dealing with like a jet engine, where then it would be important for like a propulsion system. But for now, we'll go ahead and hand wave them away. Our system, this will be our combustion chamber, reaction chamber. We're going to take some fuel. We're going to mix it with air. Air is, of course, our nitrogen and oxygen. And we're going to draw our standard thermo system where we could have possible work going out in terms of power. We can have possible heat transfer in terms of heat in. And then we'll have the products coming out. We know that's going to be water, it's going to be carbon dioxide, it's going to be nitrogen, and it's going to generally be oxygen. So those are going to be the main things that we have coming out. Now, what I want to do is I want to go ahead and note that for a nomenclature, I'm going to always use subscript R for the a subscript P. And so we're going to go ahead and set up our conservation of energy equation now that we'll probably use. And we're going to note, like on the previous slides, this is going to be on the molar basis, so per mole. And so writing out the full conservation of energy equation, dE dt, we've assumed steady state this goes away. We then have the heat transfer rate in minus the rate of work out, which is our power. And then we have the sum of all of the flow rates. We're going to replace mass flow with mole flow. And on the inlet side, we have the reactants. And so we have the sum of all of the reactants coming in, and then we have to deal with the energy. So in terms of the energy, we have the molar enthalpy at the given temperature, and we'll note pressure, so that's our state, minus the enthalpy of the reference value at that given point, plus then the enthalpy of formation at that point, or for that substance. Then we could have kinetic energy and potential energy. We'll note that this is all. And then we'll have to subtract out everything that's leaving on the product side. So all the flows out are the products. So mole flow rates of the products summed over all of the different components. We now have the enthalpy at each of the states. So temperature, pressure, minus then the reference enthalpy, plus then we have the enthalpy of formation for each of those substances, plus V squared over 2 plus GZ for our complete energy equation, and we'll note that this is for the products. And say, well, we can get rid of the kinetic energy, we can get rid of the potential energy. That's just not going to be that useful to us. And we could probably neglect work for right now. We'll say most of it was just going to be heat transfer. So this is just going to be the combustion chamber. Downstream could be our turbine. And so this is going to be the setup that we will want to use. Now what we're going to do is we're going to solve per mole rate of fuel. And so we want to solve, actually I should note that this would be per mole rate. And the reason we want to do this is we'll see that it becomes really useful for tying together our stoichiometric balance and our mass balances by doing it in this way. And so rearranging this equation, we'll have 0. This is going to equal the heat transfer rate in. We'll do per unit mole rate, flow rate of fuel. Plus then, now we now have the sum of all of the mole flow rates of the reactants divided by the mole rate of the fuel. Enthalpy at the state, T comma P, minus the enthalpy of the reference, plus now the enthalpy of formation, and then minus all of the molar flow rates of the products divided by the mole flow rate of the fuel. Then again, we have all of the enthalpies, so state, temperature, and pressure, minus the reference enthalpy, plus the enthalpy of the formation, and the basic conservation of energy equation. Now we could just resolve this. If we wanted to solve for the heat transfer rate in, what we would see is we would get the products minus the reactants. I'm assuming that you'll be able to see how that comes together. Now, what I want to show is why did we solve this per mole rate of fuel? Well, when we did our stoichiometric balance, we had 1 kmol of fuel plus then AX times the quantity of air. And we'll write this all out here in the next few slides. This goes to then BH2O plus CCO2 plus, we'll have AX times 3.76 N2 plus AX minus 1 O2. So this is going to be the general form that we have. Per fuel. This equation up here is now solved on a per unit flow of, well, I should say per unit molar of flow for the fuel. What we can find is that if we wanted to say solve for the per individual flow, so we'll do could do flow rate of O2 in. So this would be on the reactant side. Do on the product side, divided by the flow rate of the fuel. And so note this is on the reactant side. Well, the number of moles of O2 we would have, well, this would just equal the stoichiometric coefficients that we have. And so we can now use the stoichiometric coefficient to help us figure out what the molar flow rates of each of our substances are. And so if we can do that, that's going to make our life easier in terms of the actual balances. And so let's go ahead and take a look at a hydrocarbon. And so we did the hydrocarbon example before. So here we're going to have one form of hydrocarbon, which would be CYHZ in terms of chemical structure. We then had plus AX. We had O2 plus the 3.76 of nitrogen. This is going to react and give us the B number of H2O molecules, plus we have C. Then we'll have AX times the 3.76 molecules of nitrogen, plus then we'll have the AX minus 1 of O2. So this was the stoichiometric setup that we had. And now what we can do is if we look at the reactants, well, we're going to have our first component, we'll have N dot fuel over N dot fuel. So our first coefficient will be 1. You'll then have oxygen coming in, so NO2 divided by N of the fuel. The N of the fuel, this will give us A times X. Since we know A by definition is going to be Z over 4 plus Y in terms of the molecule structure, we can then multiply that by X. And so we can see that we can get all of these molar flow rates. And so we can do N of N2 over N dot of the fuel. This is going to be equal 3.76 times A times X. And we can repeat this for the products. And so in terms of the products, we'll have H2O divided by fuel. This is going to equal, in this case, B, and B is going to be Z divided by 2. And then over N dot fuel, this is going to equal coefficient C, which from our balance before was just equal to Y. Then we can do O2 in the product side, divided by N dot fuel, so equal A X minus 1. And in terms of A, this is Z divided by 4 plus Y times now X minus 1. And then we'll have the molar flow rate of nitrogen over the molar flow rate of the fuel. This is equal to 3.76 times A times X. And so we see where all of the stoichiometric balance is going to come into play in terms of our first law accounting equation. We can now bridge the gap between the chemistry setup and our energy setup. And so we can now figure out the flow rates. We can now go ahead and figure out all of the enthalpies. Once we do that, we can figure out the amount of heat that's being released. And then since we know the molar flow rate of fuel, we could then back out how much of mass of fuel would we need, because we would know, say, the molecular weight of the fuel, and we'll be able to then scale the. Now that's exactly what we're going to do in the example problem here, but I want to point out a few things. And so what we're going to do is just put it in the kind of last textbook form here. And so we'll see is that if we have Q dot in per molar flow rate of fuel, what this allows us to do is now we'll have the sum of all of the individual products divided by the sum, or divided by the individual, or the mole flow rate of fuel. Now we'll have the enthalpy of the state minus the reference enthalpy plus then the enthalpy of the formation minus then we have the sum of all of the reactants over the fuel. Then we have the enthalpy minus H ref minus, this should be plus enthalpy of formation. And so this is going to be to figure out how much heat that we would get in. And so if we did this on the molar flow rate, they could then do Q dot in. This would equal Q dot in over N fuel. And then you could multiply this by whatever flow rate you needed. So if you needed a certain amount of fuel, well, then you could use this to now solve for the molar flow rate of fuel. And then you can also note that the number of moles, you could relate that to your molecular weight. And so remember, mass should equal number of moles times molecular weight. And so if we then scale everything, we can figure out the mass flow rates of fuel once we know what the molar flow rate of fuel is. Now, what I want to point out about this equation that's hidden in the details is that we have this summation for both our reactants and products. So remember, on the reactant side, we'll have fuel, and then we'll have oxygen plus the 3.76 of the nitrogen. And so on this side here, so reactants, we have fuel, we have O2, and we have N2. And so we have 3 different species to account for, plus 3 enthalpies for each of those. So we're going to have 9 enthalpies we have to look up just on the reactant side. And on the product side, we'll have CO2, we'll have H2O, we'll have N2, and we'll generally have O2. So we have 4 there. So we have 4 species here, plus 3 more. So there's another 12 enthalpy lookups. And you can see where this gets to be a little bit tedious. Now, what we'll generally note is to help us on the reactant side, what we generally assume is the reactants coming in are going to be at the reference temperature, particularly involving the fuel. So generally what we're able to do is say the molar enthalpy of the fuel. Well, we can say, well, this could be enthalpy minus enthalpy of reference. We generally say this kind of is small, and what we generally want is just the molar enthalpy of the enthalpy of formation. So H bar fuel, we generally can kind of approximate with just the enthalpy of formation. Okay. Now, if that's the enthalpy of the formation, where do all of the other enthalpies come? And the answer is, well, we have to go to the textbook. And if we think about what we talked about, everything being ideal gas, everything should be related to just temperature. And so when we did this before, we had for air, we went to table A17. We found enthalpy as just a function of temperature, and life was good. Now what we're going to do is we're going to do something similar, but we're going to scroll down to table 18. We're going to see table 18 is of nitrogen. And for nitrogen, all of them were in molar enthalpy. So if you ever had to use the tables before to figure out like a different gas other than air, how the variable specific heats worked, and you looked up your nitrogen, well, it was in the molar version. The answer to why your textbook gives it to you in the molar version is because it is going to be using these for combustion. And so if we looked up our standard temperature, 25 degrees Celsius, that's 298 Kelvin, we're then able to read what the standard reference value is. And then we could figure out whatever our final temperature is. We can look up the molar enthalpy at that state. So if we can do it for nitrogen, we have two tables of that. The 19 is going to be of oxygen. So now we have nitrogen, oxygen, that was our air coming in. And then if we continue scrolling down, we'll then have CO2. CO2 was one of the product gases we had. So we'll be able to get all of the properties for carbon dioxide at different pressures and different temperatures. We have one for carbon monoxide. We're not going to worry too much about carbon monoxide. We have one table for hydrogen. We're not going to focus on hydrogen, but now we have water vapor. And so we can now get the enthalpies of water. And so if we go back into what we were looking at, well, we said we needed CO2. We have a table. We have water. We have a table. We have nitrogen. We have oxygen. We have nitrogen and oxygen. All of those are going to be found in tables A18 through 23, and the later tables are going to actually be where you can find the enthalpies of formation. So this is where you get the enthalpies of formation. Now, the last thing I'm going to note is for solving homework problems, what we're generally going to do to make your life easier is we will tell you what the temperature of the products are, and we'll tell you what the temperature of the reactants are. A lot more easily. We'll show probably end of this week, beginning of next week, some cases where we are looking for this temperature, and we can see that it becomes a much more complicated process because you're now going to have to iterate, but you're going to have to iterate across 4 different tables. And so it gets to be a little bit tricky. Okay, so that's where we're going to end today. In terms of our discussion of energy. On Thursday, we're going to work an example problem of the first law, so we'll be able to apply all of these details. But that's where we're going to end it for class today. If you otherwise, enjoy the rest of your evening, and I will see you on Teams for lab this week.